Today's topic is stationary waves, but before going into the stationary waves, I want to discuss about superposition and wave interference. Okay, so if you have a wave, here you can see a wave which can be represented by green line, and this wave is traveling. So when this wave is traveling, you can see another wave uh, that can be represented by blue dots. So when these two waves traveling, they meet together and they interfere. So this interference or superposition is very important to understand stationary waves. Okay, so when these two waves meet and superimpose, we have a resultant wave which can be seen by this red thick line. So you have maximum amplitude at one point and zero amplitude at another instance. So a uh, similar procedure can be seen in the formation of stationary waves. So a stationary wave, contrary to a progressive wave is a wave which carries energy from one place to another. Stationary wave does not carry any energy from one place to another. So if you have a stationary wave that is formed between 2 points A and B, between these 2 points, the stationary wave is not carrying any energy. And a stationary wave can be represented by diagram similar to this. So this is stationary wave. In a stationary wave, you have points where there is minimum amplitude and points where you can observe maximum amplitude at different instances. So the points where you have minimum amplitude are called nodes. The points where you have maximum amplitude are called antinodes. Let's see more about these nodes and antinodes in detail. So a stationary wave are formed when two identical waves, that means they have same frequency, speed and amplitude, but traveling in opposite directions meet and superimpose. So we need to be careful that it is same speed but not same velocity. Again, this usually happens. A stationary wave is usually formed when a wave is reflected of a boundary. So a standing wave does not transfer energy. As I have discussed before, standing wave does not transfer. Standing wave is nothing but stationary wave, does not transfer energy. It consists of two traveling waves that transfer energy in opposite directions. So the standing wave itself transfers no energy. So basically doesn't mean that the waves that constitute a stationary wave does not carry energy. They carry energy, but since they carry energy in opposite directions, the resultant energy transferred from one point to another is equal to zero. So its stationary wave is always associated with a resonance. So resonance can be best understood when you do a simple experiment. So the experiment goes like this: when you have a tuning fork above an open-ended air column, and you vibrate the tuning fork by keeping it on an open-ended air column, you can see for a particular length or for a particular frequency, you can hear a loud sound. Okay, hearing of this loud sound is nothing but resonance. Condition for resonance is driving frequency should be equal to natural frequency, and the lowest frequency at which resonance occurs is also called as fundamental harmonic. So in this chapter, instead of using the word resonance, we will be using the word fundamental harmonic or harmonics. So resonance is when the amplitude of a particular frequency is increased. So you can also observe resonance without any equipment. So if there is a fan or something switched on in your room, you can keep your hand closed like this and keep it near your ear. So if you keep your hand like this and keep it near your ear, what you're having is a two open-ended pipe, something similar to a two open-ended pipe. So here I have an open end, here I have an open end. When keeping it near the ear, some frequencies are the amplitudes of some frequencies are increased. So you can actually hear some sound, or you can actually hear some frequencies of the air flowing around us. So it's an example of resonance. What you're doing, you are increasing the amplitude of certain frequencies. So when a standing wave is formed with the longest possible wavelength, when a resonance is observed and that particular resonance have longest possible wavelength, it is called first harmonic or fundamental harmonic. Also remember, frequency is inversely proportional to wavelength. From the formula V is equal to F lambda, since velocity of a particular wave remains constant in a same medium, frequency is inversely proportional to wavelength. So for the first harmonic, you have longest wavelength or shortest frequency. So all harmonics have frequencies that are integral multiples of fundamental frequency. As I said, fundamental frequency is the least possible frequency, or so all the other harmonics, all the other resonances formed in the same pipe or same string have multiple can be observed at integral multiples of fundamental frequency. So the points on the string are in a pipe where destructive interference happens between two waves. The displacement is always zero. We call these points nodes. The distance between two consecutive nodes is half a wavelength. Similarly, halfway between two nodes are points where due to the result of constructive interference, the displacement gets as large as possible. These points are called antinodes. Note that the nodes always have zero displacement, whereas near the antinodes we have maximum displacement for an instant of time. So this is an example of formation of stationary wave. So you can see the wave represented by red lines is a wave that is moving towards right. The wave represented with the blue line is a wave that is moving towards the left hand side, and the green line is the formation of stationary wave. It's a resultant of these two waves. So when two waves have zero phase difference, they are undergoing constructive interference. When the two waves, as they are moving, have 180 degrees phase difference or lambda by 2 phase difference, you have lambda by 2 path difference, you have a destructive interference. And during destructive interference, you have a wave with zero displacement. So if you see this point, and this point, you have zero displacement at this point in both the circumstances. And here t is equal to t by 2. So we are observing this graph for a complete cycle. So at this interval, at t is equal to t by 2, you have again constructive interference, and if you see at the same point, you have zero displacement. Then again at t is equal to 3t by 4, you have complete destructive interference, and again the displacement here is 0. And at t is equal to t, we are back to the initial stage where a constructive interference is happening, and at this particular point we have 0 displacement. These points on a wave are called node, and these points are called antinode. So at a point where an antinode is formed, you can have 0 displacement and maximum displacement. But at a point where nodes are formed, you'll always have 0 displacement. And usually the stationary waves are represented like this. The stationary wave is represented like this. Okay, so this represents a profile at t is equal to 0 and t, and this profile, the wave, the line, straight line without any amplitude, is a profile at t is equal to t by 4 and 3t by 4, and this one, the other one, is a profile at t is equal to t by 2. So we represent stationary wave as a combination of two waves. So the ends of standing wave can either be nodes or antinodes. These ends are boundary conditions determine possible shapes of a wave, possible shapes of a stationary wave. There are three possibilities, that are two fixed ends, two open ends, and one open and one fixed end. The first possible frequency is, the first possible condition is a wave formed when there are two closed ends. So whenever we have closed ends, we have nodes at the ends. So this is a string. Stationary wave is formed on the string. So at this point we have a vibrator. It is vibrating, and this wave travels from this vibrator to the other end, where it is reflected back. So this reflection of the wave forms stationary wave. So this is a node, this is a node, and this is an antinode. So this is also called Mills experiment. This experiment can be used to study the relationship between frequency, length, tension, and thickness of the wire. So when a stationary wave is formed on two closed-ended pipe or a string, you have two nodes. The first possibility is at both the closed ends you have two nodes, and in the center you have an antinode. So this is the first fundamental harmonic or first harmonic. So it has one loop, and the distance between two nodes is lambda by 2. Similarly, the second harmonic has two loops and three nodes and two antinodes. So here you have a node, here you have a node, and here you have a node. The center of these two consecutive nodes, you have antinodes. So this is the second harmonic. And we can similarly draw the third harmonic. You have another loop that is forming. This is the third harmonic. So let's see detailed diagram. And another interesting thing to observe is, when a stationary wave is formed, the particles here are trying to come down, the particles here are trying to move up. So the displacement of the particles are in opposite directions. When a stationary wave is formed, the displacement of the particles are in opposite directions. So points within consecutive nodes have velocity in the same direction, and points in the next loop have opposite velocity directions. So here you have the particles, all of them are coming down, and here the particles that are trying to move up. So the displacements and velocities in the consecutive loops are in opposite directions. So this is the fundamental frequency, this is the second harmonic, third harmonic, fourth harmonic, fifth harmonic and sixth harmonic. So if you observe, these all formed on the same length. So here we are keeping the length constant. So all of these are formed on a wire of length L. And if you remember, the distance between two consecutive nodes is lambda by 2. So here L is equal to lambda by 2. So lambda is equal to 2L. And here this is lambda by 2 plus lambda by 2. Observe that wavelength of the second harmonic has changed. As the wavelength of the second harmonic has changed, L is equal to lambda by 2 plus lambda by 2, which is nothing but lambda. Lambda is the wavelength of the stationary wave that is formed. In this particular case, again the wavelength has changed, and now wavelength is equal to, length is equal to lambda by 2 plus lambda by 2 plus lambda by 2. So L is equal to 3 lambda by 2, or in other words, lambda is equal to 2L by 3. And similarly, fourth case, lambda is equal to 2L by 4. So wavelength is changing in the form, we can write a formula, general formula, where lambda n is equal to 2L by n, where n is the nth harmonic. So math involved, just we have discussed. I will come back to these things when I'm discussing a problem. So you can also have two open-ended pipe, or two open-ended string is not possible. You can have a two open-ended pipe. So what you have is, you have a signal generator where you are producing an antinode at this end, and an antinode is formed at the other open end also. So whenever you have an open end, you have an antinode. Antinode is going to form. So it's also called a Kunst tube. This can be used to calculate speed of sound. So here you can see nodes forming at a regular intervals. By calculating these nodes, by sending a sound signal and calculating the nodes, we can understand which harmonic it is, and we can calculate the velocity of sound by using the formula V is equal to F lambda. We can measure lambda from the experiment, and then as we are using a signal generator, we know the frequency, and hence we can calculate the wavelength, the velocity of the light, velocity of the sound. So this is your first possible scenario: two antinodes at both the ends and node in the center. So here length L is equal to lambda by 2. Here the distance between antinode and node is lambda by 4. So this is also lambda by 4. Total length is lambda by 2. Similarly, this is lambda by 4, this is lambda by 4, and this is lambda by 2. Total length is lambda. And third one, you have 3 lambda by 2, lambda by 2, lambda by 2, plus lambda by 4, lambda by 4. So you have 2 lambda by 2 plus 2 lambda by 4, that is 3 lambda by 2 is equal to n. And fourth one, if you can see, observe the pattern, it is 4 lambda by 2. Fifth one will be 5 lambda by 2 is equal to n. So common representation can be L is equal to n lambda by 2, or it can be written as lambda n is equal to 2L by n, and n represents the nth harmonic. So we have a similar formula, but the diagram the representation, wave formation is different. So for a two closed-ended pipe, we have two nodes at both the ends. For two open-ended pipe, we have two antinodes at both the ends. So we can also see a simulation of stationary waves on two closed-ended strings. So a simulation looks something like this, a Phet simulation. So I can oscillate this string. This is how a stationary wave is formed. So there is no energy transfer between these 2 points. So this is an example of a stationary wave. Moving on. The last case, you have one closed and one open-ended pipe. In one closed and one open-ended pipe, you have node at the closed end and antinode at the open end. So the distance between node and antinode is lambda by 4. You can see this is only 1/4 of a wave. So this is your first harmonic. Resonance tubes are good examples of one closed and one open-ended pipe. So here you have lambda by 2 and lambda by 4. So the second harmonic has length which is equal to 3 lambda by 4. And similarly, the third harmonic has wavelength which is equal to L is equal to 5 lambda by 4. Here you have 3 lambda by 4 and here L is equal to lambda by 4. So the wavelength is changing. So you can say here lambda 1 is equal to 4L. Here lambda 3 is equal to 4L by 3 and wavelength here lambda 5 is equal to 4L by 5. So if we see the wavelengths are changing, but it is not changing regularly. In the previous case, lambda is decreasing in the order 2L, lambda 2 is equal to 2L by 2, lambda 3 is equal to 2L by 3 and so on. Okay, but here wavelength is changing from 4L to 4L by 3 and 4L by 3 to 4L by 5. So we are only considering, when we are taking lambda n, we are only considering odd values for the n. So here n is equal to 1, 3, 5, 7 and so on. So we have only odd, the frequencies or wavelengths are odd multiples of initial frequency or initial wavelength. So that is something that we need to keep it in mind. So let's do a simple problem and wind it up. So remember, as I was telling, you only have odd harmonics for one closed and one open-ended pipe. So a musician maintains stationary sound wave with a node at the mouthpiece. So you have a node at the mouthpiece and an antinode at the other end. The lowest frequency of the sound of the instrument can be produced is 92 Hz. Which different frequency of sound can be produced by the instrument? So this is an instrument. It's more like a flute. You have a node at one end and an antinode at another end, and your fundamental frequency is 92 Hz. Your fundamental frequency is 92 Hz. So this is the question they are giving, and they are asking which frequencies of sound can be produced. So from the previous slide, I have just told that only odd multiples are possible for nodes for one open-ended and one closed-ended pipe. So you only have F3, that is 3 into F1, F5, that is 5 into f1 and f7, that is 7 into f1 should be your answers. So let's see, we have 4 options, and in these 4 options, see which are the multiples of 92. We need only odd multiples. So the odd multiples will be 92 into 3, that is 276, 92 into 5, that is 460, and 92 into 7, that is 644. So only option C is correct because it's only odd multiples. Five into 92 and 7 into 92. So we can do the same thing by representing them, by seeing the representation. So here this is lambda by 4, this is node and this is antinode, and L is equal to lambda by 4. So lambda is equal to 4L, and as V is equal to F lambda, F is equal to V by lambda, and lambda is equal to 4L. So F1 is equal to V by 4L. Similarly, F3 is equal to V by lambda 3, and lambda 3 is nothing but 4L by 3. So you have 4L by 3, which can be represented as 3V by 4L. As V by 4L is F1, this becomes 3F1. So that's how it goes on. So similarly, F5 will be 5F1. So with this problem, I'll end my class for today. I have done this as a form of revision rather than explaining for a new class. Yeah.